This is Physical Science 2, Chapter 12, Part 3 on Earth's internal processes. In this portion of the video lecture, we will be discussing the Earth's interior. How do we know what the inside of the Earth looks like? We know what the surface looks like, we know what the ocean floor looks like, but how do we get deep down inside the Earth to see what the Earth is made out of? If you remember from our last video lecture, we discussed the different types of seismic waves. And seismic data from earthquakes around the world is used to infer the interior structure of the Earth. Remember, we had two types of seismic waves. We have body waves, which were the primary and secondary waves. Those travel through the Earth. And surface waves, the L and the R waves, travel around the surface. So what we do is we use those body waves almost kind of like an X-ray to see what's going on inside the Earth. If you can remember, primary waves can travel through substances that are either solid, liquid, or gas. And remember, secondary waves, or S waves, can only travel through solid materials. So we can use that information with those two types of body waves. And when seismic stations all over the world, when they record earthquakes happening, there was some instances where earthquake waves would either seem to speed up or slow down and arrive at stations at different times than they had predicted. And there was an idea that these earthquake waves speed or slow down with changes in density of the material that they traveled through. So earthquake waves would move through a material very quickly if it was solid or compact. And there would be a little bit of slowing down if that material was a liquid or a gas. So what we look for in trying to infer the interior of the Earth is what we call discontinuities. A discontinuity is a density change between the layers of the interior of the Earth. The first big boundary, the first density change that we notice using primary and secondary wave data is what we call the Mohorovičić discontinuity. So discovered by Russian geologist Andrija Mohorovičić. We just call it the MOHO. Plus it's more fun to say. The MOHO is an interior boundary that separates the crust from the uppermost mantle. So the Mohorovičić discontinuity, the MOHO, is the first place inside the Earth where we see a change from all solid to a little bit liquid. Also, when seismic stations around the world record the instances of earthquakes, there are some stations that seem to not get any information. The primary and secondary waves travel through Earth in all directions from the focus. Remember, the focus happens underneath the surface, and all the waves come out in all directions, just like you chuck a rock in a pond, same idea. On the Earth, wherever an earthquake is, between 105 degrees and 140 degrees from the epicenter of that earthquake, there are no P waves that are recorded. We call that the shadow zone or the dead zone. There are no P waves recorded in the shadow zone. Now you might think, how in the world, if primary waves can travel through solid, liquid, or gas materials, why wouldn't they be able to be registered all over the Earth? Well, in this diagram here, you kind of see what happens on the inside of the Earth when these primary and secondary waves come through. So primary waves, we have several instances of primary waves having their energy come out in all different directions. If you start throwing rock after rock after rock in a pond, sometimes some of those waves from the rock in the pond will combine and get really, really big, and sometimes those waves will hit each other in opposite crest to trough and they'll kind of cancel out. Now that's what's happening inside the Earth. And so in the P wave, in the shadow zone, where there are no waves recorded, is because that's where we have all of this refraction of the primary waves away from each other. So we can use that to figure out which part of the Earth is solid and which part of the Earth is liquid. We know that the inner part of the Earth, the very solid inner core, refracting P waves that travel through the Earth indicate that we have an inner core that is dense and solid. When we talk about the composition of the Earth's layers, the crust, the lithosphere, the part that we're standing on, and the uppermost mantle is composed of what we call silicate minerals. We'll talk a little bit more about those in our next unit in more detail. But silicate minerals are very light colored and they have a pretty low density. The lithosphere sits on the very upper part of the upper mantle, and we call that part the asthenosphere. The asthenosphere is a weak, kind of plastic-like layer that the lithospheric plates move around on. So when we discussed plate tectonics in our first section, that's what the lithospheric plates are moving around on, is the asthenosphere. You can kind of think of the asthenosphere as like a layer of chunky salsa. Some of it's liquid, but there are still chunks of rock in the asthenosphere. So it is weak and it can be deformed in a plastic-like manner. But this is what the lithospheric plates move around on. The asthenosphere is right at that moho boundary where we go from solid, compact crust to a little bit kind of liquidy, chunky salsa-like consistency. Then below the asthenosphere, the mantle is mostly liquid, is composed of silicate minerals as well. Again, silicate minerals are very light in color and they're very low density. And as far as we can tell, the inner and the outer cores are heavy materials. They're mostly composed of metallic materials. And as far as we can infer, we believe that the inner and outer cores are made of iron and nickel. And remember, the inner and the outer cores, the outer core spins around the inner core, and that creates our magnetic field, which, remember, protects us from a lot of different types of solar radiation and space debris. This has been Chapter 12, Part 3 on Earth's internal processes.